guys, welcome to our last session on stars, and what I want to do is just kind of go over and give you a kind of a nice review. Now, remember that you also need to be checking Blackboard for what's on Blackboard, and there's a sheet that says Star Review, and you definitely want to go ahead and pay attention to that. Remember, after we're finished, you're going to have a test. Remember that your final is comprehensive, so don't forget to continue remembering the stuff that we cover. So, guys, let's talk about stellar evolution review. On Blackboard, there is actually a sheet that talks about what you need to know for your star exam. So you might want to make sure you have that. And they get into probably a little bit more detail than what we're going here. And one of the sessions that we will do is a nice review session. But here I just kind of want to go over what I consider important and just kind of bring back what we've talked about for this unit. So let's just kind of start back with our stellar distances. You know that distances to the stars and beyond are certainly measured in light years. And remember that a light year is the distance that light travels in a year. It's not a measure of time. It is certainly a measure of distance. And one of the hardest things, I think, in looking at astronomy is really looking at how far those distances really are. I mean, it's almost inconceivable. Because if we look at what's going on within our solar system and thinking about that in terms of light years, we're something like 1.6 times 10 to the minus fifth light years. Very, very, very tiny distances. And yet, when we look at distances within the stars, our nearest star is 4.3 light years away. And so that's why we had to come up with some kind of unit that allowed us to talk about these really, really, really large distances. Then we talked about spectroscopy, which is a study of light. It's broken down into its component parts. And if we didn't have this, we wouldn't have anything in terms of what we know about stars, because the only way we have of looking at the stars is looking at the light that comes to us from those stars. And so if I look then at what I can determine from the stellar spectrum, I can come up with the chemical composition, the chemical abundance, density and pressure, temperature, rotational speed, radial velocity, size, all these kinds of things that are going together to give me an indication of what indeed is going on with that star, and as we've talked, where that star is in its evolutionary process. And you've seen this picture before, but that's just the sun's spectra. You see those dark lines in there, which are absorption lines, and then you get those continuous spectrum then that's on top of that. And the stars are classified based on their spectra. And the primary reason that they're going to look different is because stars have different temperatures. And remember, guys, those different temperatures deal with what's going on in the outer envelope of the star, the atmosphere of the star. Because remember, we can't see what's going on within the core. We can only look at what's going on within the outside of the star and then say, okay, based on that, let's see if we can come up with models and then do explain what is going on within the core of that star. And certainly you know that different temperatures are going to cause chemicals to behave differently. They can either become ionized, they can go ahead and completely be separated so that you only have free electrons and the nuclei is roaming around. So different lines are going to show up in the spectra depending on what the temperature of that outer envelope of that star is. So the hottest stars tend to have very little lines in their spectra because all of the electrons have been stripped off, so the electrons are not there to produce that. Now remember, guys, that stars are essentially made of hydrogen and helium, and we're only going to have small differences in those heavier elements. And again, for our purposes, heavier elements are defined as anything above helium, because we know that everything within our universe had to be made within those stars, within the explosions or within what was going on within the core as those nuclear thermonuclear reactions were building up smaller nuclei into large nuclei. We're going to talk in the next unit about galaxies and cosmologies and what was the universe like at that very, very, very young age. Also remember, in general, the younger the stars, the greater amount of heavy elements that are going to be present throughout that star. And when I say the greater amount, we're still, even our sun, which we think is a third-generation star, we're still talking mostly hydrogen and helium with less than 2% of everything else. So the hottest stars are going to be classified as O-type stars. And remember, it goes from an O, B, A, F, G, K, M, and then an L. And within each one of those classes, then, you have those subcategories. And remember, I had you look at stellar spectra and actually sent you to a website where you were able to go ahead and see how well you did at classifying what those stellar spectras were like and what chemicals were in the outer envelopes of the star. And then probably the basis of what we were doing within this unit really comes down to what's happening with that star on the HR diagram. And that's called the Hertzsprung-Russell diagram. And remember, it's a plot of absolute magnitude versus spectral classification, or you can get brightness and temperature. The HR diagram, as we have talked, is used for evolutionary sequences and for identifying those characteristics and behaviors of those stars. Now remember, guys, it's not physically in space in terms of where they lie on the HR diagram, but it's based on their characteristics of magnitude and spectral classifications, or brightness, and looking at the temperature of that star. And based on where they are on the HR diagram will tell us something about what's going on within that star. Is it doing what a normal star is going to be doing, which is basically converting hydrogen into helium, or is it already off that main sequence line and doing something different? So this is a picture of the HR diagram. Notice that you're looking at luminous stars that are very bright on the left side, on the upper left side, and then dim stars on the lower left-hand side. And then on the lower left-hand side, you're looking at very hot stars, meaning you have very high temperatures, and then very cool stars on the lower right. And I can't stress, guys, that remember, we are talking about the outer layers of that star. We don't have a clue. I mean, we do have a clue, but I mean, in terms of looking at this, we're not looking at what's going on within the star itself, nor are we certainly looking at within the core. This is just the part of the star that we can observe by looking at its spectra. You have this big, huge kind of HR or main sequence line, or main sequence kind of a band coming down. And notice that you have really hot luminous blue stars at the top and really cool red dwarf stars at the bottom. And as you move from the upper left to the lower right, the frequency of those stars certainly increases. So I have huge numbers of red dwarfs, very little of these really hot blue stars. Now when you look out in the sky, we see lots of hot blue stars, guys, but we're, billions and billions and billions of stars. Even just a few percentages out of those billions and billions of stars is going to show up. And a lot of those red dwarfs, those lower, really small, tiny stars, we can't see unless they're really close to us, because they are very small and they are very dim. And so it's very hard to go ahead and observe them in the sky unless they're real close. Now, there's the then main sequence line. And then notice as I go to the upper right, I'm getting the red giants and red supergiants. Those stars are very, very bright, but they are very cool. And the reason they're so bright is because they are incredibly massive. If you set one of those red supergiants where our sun is, the edge of that red supergiant is out past Jupiter's orbit. I mean, these are incredibly massive stars. So even though they have temperatures that are very cool, it's just the sheer volume of that star that causes them to be so bright. And then if you look kind of in the lower middle left, you see what's called white dwarfs. And that's another part of the star as it's gone through its evolutionary sequence. And that's going to be the center of stars that we see that have gone ahead and basically evolved, formed planetary nebulas, and then what's left as that white dwarf. So if those stars are on the main sequence line, then they are converting hydrogen into helium, which is what a normal star does. And then they can start evolving off the main sequence line, and that's when that core is going to start changing. And what determines what happens to that star, and I can't say this enough, guys, is the original mass of that star. And we're making the assumption that mass is not going to change. It's not going to have mass added to it from another star or anything else like that. This is just another plot of the HR diagram. Notice you're looking at luminosity versus temperature. Luminosity is, again, related to the brightness. So we can talk about sizes of stars. We can talk about supergiants, which are more than 100 times the sun. Giants, which are about less than, our sun, around 100 times. Main sequence stars are from 0.1 to about 20, 30, 40 times our sun. White dwarfs are from 0.01 to about 0.1. And then you have these little brown dwarfs that are really not on the main sequence line. They're kind of right below it. And you can see that they're not very big at all. They're certainly not even a substantial amount of the size of our sun. And you will see, and as we've talked, guys, you're going to see these numbers that are going to vary a little bit depending on what source you're looking at. When we did it, I kind of just used the idea of you had, these red dwarfs, you had these brown dwarfs, you had medium-sized stars, which were basically stars like our sun. You had large stars, and then you had massive stars. And that's what we looked at on the main sequence line. And then once they evolved off the main sequence line, that's when they became these red giants, these red supergiants, these neutron stars, these white dwarfs, those kinds of things. I also want you to remember that a star spends about 90% of its time on the main sequence line converting hydrogen into helium. It's just doing what a normal, everyday garden variety star does. The only thing that the main sequence stars differ by are certainly mass, and like I said, that's a biggie. And then, depending on whether they're a first, second, third generation, fourth generation star, some of that composition. But even then, guys, we're only talking about less than 2-3% of everything else that's heavier than hydrogen. Heavier than helium. And like I said, of those two, mass is certainly by far the biggest feature. Now remember, too, guys, that in terms of looking at what's going on within that star, this is on the main sequence line, it's essentially in hydrostatic equilibrium. So that means the outward pressure that flows out from the core, is going to be equal to that gravitational collapse that is trying to pull it in. And so if a star is in hydrostatic equilibrium, then the outward flow of energy is equal to the gravitational force coming in. Then, if something happens, that equilibrium is disturbed, the core collapses, that star is going to get smaller. If you have then energy that's produced in the core, it's going to tend to cause that star to expand as it travels outward, and then when it expands outward, the star itself is going to go ahead and cool off. And that's just kind of what I was talking right here. Star's life is always a battle between gravity causing that star to contract. And when we say that, generally we're talking about what's going on within the core. But as we've talked, you realize that what happens in the core will eventually make its way out to the star and to the outer envelopes of the star. And so eventually, if the core collapses, the rest of the star will collapse. If the core expands, the rest of the star is going to expand, but certainly not on a one-to-one basis in terms of time frames. Also remember that the bigger the star, the shorter its lifetime. Our sun is a G2 star, and we've been on the main sequence, so we've been burning hydrogen into helium for about 5 billion years. And we're going to continue burning it for another 5 billion years. If we talk about stars that are extremely small, like those red dwarfs, they are going to be possibly on that main sequence line for trillions of years. So we have never, ever seen those things evolve off. If we talk about some of these really big, hot blue stars, they may only be on the main sequence line, a couple of million years. Remember, the bigger they are, the faster they're going to use up their energy, and the faster they're going to go ahead and evolve off. Protostars are stars that are in the process of forming, and remember that they form in really dark, cold molecular clouds, and they usually form in clusters from the clouds then that are found in the spiral arms of our galaxy. We'll come back a little bit more to these clusters in the next unit when we talk about galaxies and what's going on there and the formation of those spiral arms. And as we've talked, remember that a star is mostly hydrogen with some helium. And once it goes ahead and starts moving off the main sequence line, its core is no longer going to be undergoing thermonuclear reactions to convert hydrogen into helium. Now we're going to go for helium into other elements. For the really large, massive stars, we'll make it all the way up to iron. For some of those medium stars that are not very big at all, we're never going to make it past carbon Certainly not in a whole lot of oxygen, unless you might have some random oxygen that is produced there, simply because of the fact that you do have temperatures and pressures high enough that occasionally that will happen. But now, if we know that elements up through iron are made up in the core, well, then we've got to explain where all those other elements have. If you look at our periodic table, guys, we have lots of elements out there. So as I have stated before, all those elements are made within the explosion of stars. So whether we're talking about lithium, sodium, potassium, all of those things, the only reason we have those elements is because of what goes on within the reactions of those stars. Not only just in the core, but then as that star then goes ahead and starts going through its evolutionary sequence, and especially when we get some of those really big supernova explosions, we get all those heavier elements that are made. So as I've said before, guys, you are made of star stuff. I like to think of that. I'm made up of star stuff, you know? A little bit more than just saying, oh yeah, it's carbon, hydrogen, oxygen molecules. I like the idea that those things came from stars. Basically, our little red stars, those little red dwarfs, are going to do nothing more than cool off and fade away. And, you know, you've got that sheet that reviews it. I want you to go ahead and you need to do this in a little bit more detail than what I'm doing, but we'll talk about that then after you have a chance to fill that review sheet out. And medium stars like our sun are going to go through several stages. You know, you certainly got the main sequence star, then you're going to go into a red giant. And then you remember when I showed you those planetary nebulas? And once that star then has leaked off its outer edges and basically the rest of the star, because of the fact that they've gotten so big and the core can't hold on to them anymore, then I have a white dwarf that's remaining at that core. And that white dwarf is contracted down to the point that it's being held up or supported by electron degeneracy pressure. And you remember those planetary nebulas really looked kind of cool when they were giving off or pulsing outward. Larger stars are going to do the same types of things. You know, they start as a main sequence star. Now, because they have more mass, they're going to go into the red supergiant. They will then go into a supernova. And as that supernova forms from the core collapsing, the rest of the star rushing down onto that core, then rebounding into this extremely large explosion, and you can generate a whole lot of energy in a supernova explosion. Then what remains then, as that core then kind of was compressed together because of the rest of the star rushing down onto it, and that's a neutron star. And neutron stars then are held up by the fact that everything now is a neutron, and so they can get much closer. Think about a white dwarf as being basically the size of the Earth or a little bit smaller. So, I mean, you got a pretty hefty density in there. A neutron star, on the other hand, is much, much smaller than the Earth. It's the size of a small city. So, you know, think what the densities are going to have to be inside that. The other thing that the neutron star has, as well as looking at the white dwarf, is these things are going to be spinning, but you know, because you have contracted that neutron star down to such a small mass, that law of conservation of momentum says that those things are spinning really rapidly. And those neutron stars have a pretty hefty magnetic field. And so you have a bipolar flow of radio waves coming out where the axes of that magnetic field then run into the poles of the neutron star. So that means if we happen to be in the way between us and the neutron star, and the neutron star then is rotating rapidly, we can then measure that pulse that comes off of that neutron star. And so a lot of times you will talk about a neutron star as being called a pulsar. Okay? And they're very, 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 very consistent over a period of time. However, given enough time, you will see them go ahead and start slowing down very, very slowly. And so you can see that, yeah, they will eventually cool off and probably eventually, given enough time, completely stop spinning. But it's going to take a long time. Then we've got these massive stars that kind of go through these other stages as well. They go through a main sequence star. They go into the red supergiant star. They certainly do the supernova. Only this time, guys, what happens when that core collapses, The rest of the star rushes in on the core, but the rest of the star is so massive that the core can't really support it. Even if we're down to the point that you're looking at neutrons, the core simply collapses beyond that point. And it collapses beyond that point enough that it basically winks out of our universe. And so what you have then remaining is a black hole, which is basically a point in space where a star used to be. And remember, we talked a little bit about Einstein's ideas and what happens when you start approaching the speed of light. And we started talking about that curved space. And so curved space and time get mixed up in that. And remember that according to Einstein's ideas, when you look at speeds approaching the speed of light, that time is going to slow, that your length is going to contract in the direction of motion, and your mass is going to increase. Well, when we get toward a black hole, that thing is so massive that your time is certainly going to be affected, your length is going to be affected. And we know that when we go back and look at these galaxies, that within the core of these galaxies, you have had very large massive stars that have gone off very quickly. And so we know at the center of these galaxies, you have these massive black holes. And that's true of our galaxy too, guys. If I look at Sagittarius, I'm looking toward the center of our galaxy. And when we get to that point, we'll go look at some pictures of what's going on. And we find that, obviously you can't see a black hole because it is curved space so much that the light can't even get out. But we can determine where those black holes are based on their effects that they're having on other materials. And we see gigantic explosions within these galaxies. And we think that that's probably what's going on when these black holes literally are cannibalizing stars within the core of those galaxies. And we see very active galaxies, in which case we find huge protrusions of material that are given off, that are streaming out of the core, and again, related to what's going on with these black holes. And it's not just one, it's literally hundreds because of all the really big, massive stars that you had going off within the core. So we're certainly not finished with these. We will come back to them as we talk about what's going on within these galaxies. And then we talked about our sun. Remember that our sun has several components to it. It has a core, a radiative zone, a convective zone, a photosphere, a chromosphere, and a corona. And that photosphere, coronosphere, and corona are more that outer envelope of our sun. That photosphere is pretty well where we're starting to not be able to see any further down into the sun. And so it's more the opaque surface. And as I've stated before, guys, for these stars, when we talk about surfaces, we are not talking about solid surfaces. We're just talking about transitions or boundaries within the star itself. Remember that our sun is just an everyday garden variety star on the main sequence line. So it converts hydrogen into helium. And so we talked earlier about that proton-proton chain. I'm not going to ask you to give me that proton-proton chain back. I am going to, though, give it to you and ask you about some things. So make sure you know what those particles are on that proton-proton chain. Then we have active regions on the sun. They include sunspots, PLAGES, prominences, flares, all those kinds of things. They all have similar longitudes and latitudes, but they seem to occur in different heights, and they always seem to be associated with really strong magnetic fields. And that's probably true of a lot of stars out there, is they're going to have very strong magnetic fields because of what's going on within those stars. Sunspots are darker, cooler regions on the surface. Excuse me. And they can at times be seen with the naked eye. Now remember, guys, we're taking 110 Earths and putting them across the surface of the sun. So when we see those sunspots with the naked eye, those things are really large. Now, guys, don't go out there and look up at the sun. That's not a good idea. However, if you're looking at the sun right on the horizon and you've got lots and lots and lots of clouds that is coming through, a lot of times you'll still be able to see that surface, and you can see that there are dots or spots on it. But because you're looking at it through a bunch of clouds, it's a little bit easier to see. It's not shining full on in the upper part of the atmosphere. It's actually coming through more of the atmosphere. Even that, guys, though, you do not want to go out and stare at the sun. That's not a good idea. Galileo went out and looked at the sun through a telescope. That did not do his eyes good. He was, partially blind the last part of his life because of that. We do know that these sunspots can last from a few hours to a few months. And if they're lasting a few months, it really works nicely because we can use those as they move across the surface of the sun to go ahead and determine the rotational period of the sun. Individual spots usually show a darker area, which is called the umbra, and a penumbra, which is a kind of lighter region that kind of surrounds that. And that's true of most shadows, guys. If you really go look at them very carefully, you'll see a really dark area, and then you'll see a little bit lighter area. We also know that they frequently occur in prominent pairs. So you may have a big spot surrounded by lots of little spots with another big spot surrounded by lots of little spots in very close proximity to each other. And generally, the two prominent spots have opposite magnetic poles. So one of them might be a north pole, one of them might be a south pole. And the leading poles are the same ones in the hemisphere, but they're opposite in the other hemisphere. So you have the northern hemisphere and southern hemisphere. And we find that those spots never cross. If they start out in the southern hemisphere, they'll stay in the southern hemisphere. They never actually go ahead and cross into the northern hemisphere. And then the next cycle, guys, they simply go ahead and reverse polarity. So we know that they're driven by the sun's magnetic field. We know there's an approximate periodic 11-year cycle from maximum to maximum. So every 11 years seem to have a maximum. And again, that's every approximate 11 years. They go from maximum to maximum. But that doesn't mean that during the point that you have a minimum, you can't get some really massive sunspots showing up, because we know that happens as well. And then you have a 22-year cycle for polarity. So one 11-year cycle, in the northern hemisphere, the leading spot might be a south pole. That next 11-year cycle, that leading pole is going to be a north pole. And so it takes 22 years to get back to that same leading pole, as opposed to just looking at a maximum and minimum. Phages tend to be clouds of calcium and hydrogen and other elements that go ahead and show up around sunspots. And they show up as bright areas that have a higher temperature and density. And when you look at them, it looks like the sun is literally opening up and spreading apart. And so I've certainly given you some URLs for looking at some of those phages as they're moving across the surface. If you haven't done that, guys, go do that. The spectrum is going to show calcium and hydrogen and not the other stuff. But again, it's only due to the temperature that is required to go ahead and ionize those particular chemicals. Doesn't mean that the other elements aren't there. It just means that the temperature isn't right to let us see it. Prominences, on the other hand, originate higher in the atmosphere, usually found around sunspots as well, but not always. And if you look at them from the side, they look like these huge flames that are protruding or rising up from the sun. Man, they are huge. They can reach all the way up in the top part of the corona, and they can last for many hours, many days, and they can dwarf the Earth in size. So if we happen to then be in the path of those things will go ahead and then run into us. And yeah, we can have really nice northern and southern lights. We can have some disruption in our radios, communication, things like that. And then we have flares, which tend to be very rapid eruptions on the surface. They can last from about 5 to 10 minutes, and they can release huge amounts of energy. And as like everything else, they tend to be most active during the sunspot maximums. Now remember, guys, just because the sun is 93 million miles away from us, that's the only reason we exist, is because the sun provides all of our energy. And so we do know that even though that sun is 93 million miles away, what happens on it has an effect on what goes on here on the Earth in terms of our weather, in terms of looking at the activity we have in the upper part of our atmosphere, those kinds of things. So, guys, it's a good thing that sun exists. Then we know we have solar winds, and those are streams of charged particles, generally protons and electrons, that are going to flow outward from the sun's atmosphere. And these are at speeds approaching 900,000 miles an hour. Look at that, guys. 900,000 miles an hour. These things simply are moving so fast the sun can't hold them. And so they managed to make it up into the corona and just leave the system. Now also remember, guys, when we talk about the sun's corona, we are talking about that outer envelope of the sun's atmosphere, if you want to think about it. And we know, again, dealing with magnetic fields, that there's a very sharp increase in the temperature as you go from the coronosphere and then the photosphere into the corona because of that magnetic field. And so the temperatures in the corona are, in millions of degrees, whereas the surface temperature of our sun is only at about 5,800 K. And it's because of that acceleration that you're getting as those particles are getting accelerated over the magnetic field. Remember that these coronal winds, solar winds, and these coronal holes are not visible in just regular light, like what we see with, but they are very visible in X-rays. And so when you look at the sun in these X-rays, you see these huge dark areas that are literally, it looks like where something has ripped off part of the sun, and that's where you're getting these really big coronal holes and where the solar winds then come streaming out of. And they can account for a huge amount of material that's coming out of the sun. 10 million tons of material leaving the sun. Luckily, our sun is really big, and that's not an issue. But keep in mind, you do have that material flowing out. Okay, guys, so that basically went through the evolutionary sequence of a small star, a star like our sun, a large star, and a massive star. Now, on Blackboard, you've got a star review sheet, so you need to go through that. We'll go ahead and get together through Blackboard or whatever. Go ahead and go over that, and remember that your test will probably be next week. You need to study well, and we'll go from there. So guys, otherwise, the next time I see you with notes, we'll go ahead and start talking about cosmology and what's out there. So I want you to go outside. I want you to look up and see what you see. Talk to you later, guys. Bye.